Welcome back, everybody. So there's the key for the homework. Start checking your answers. I'm going to scroll down a little bit. Pause if you need to on the video. Okay, there's 8 and 9.
Oh, I love that. I love it when I saw organizing. I have questions for number 8.
Yes.
I just put the equation that they gave us in my calculator and then put
Do it across.
an x value, I think, and then did the intercept.
That's totally fine.
That's fine, okay.
Yep. Ask questions where we need to. Does anybody still need 5, 6, or 7? Let's scroll down then. There's 8, 9, 10, and 11. To 11.
You go over?
Yeah.
I didn't get that one.
Okay, so we do log of 72 minus log of 2x over 3 equals 0.
Why would you not just multiply 3 over to the other side?
Because it's within the log. You can't do that to evaluate that. Since it's within a log, you can't just multiply over to the other side. You can't do inverse operations. Because technically, order of operations says the log is working on it first. Because the log is like an exponent. Although I'm looking at something now. I'm going to try something different in the end and see if it works. But I'm going to go this route, the route that they have on the screen, because what we're looking at here is that if I've got subtraction, that means division, right? So really, this is like taking log of 72 divided by 2x over 3, right? We just got to figure out what that thing is. So if I'm looking at 72 divided by 2x over 3, well, dividing a fraction is multiplying by the reciprocal, so 72 times 3 over 2x. All right, so 3 over 2x, that would be, let's get the 2 out of the way, divide this by 2, that's 36. Cross simplify there, 36 times 3 is 108, and then 108 divided by x. So that's where we get the 108 over x. So log base 10 of 108 divided by x, and now we change it from logarithmic form into exponential form. So this is a base 10, so we say 10 to the 0 is equal to 108 over x. Well, 10 to the 0 is just 1, is equal to 108 over x. So x is equal to 108. Okay. I want to try something though. I want to take a different look at this problem. And if I had started out this way, log of 72, oops, that's 27. Log of 72 minus log of 2x over 3. Okay, because I think if we make the log bases the same, and it's the same thing on both sides, you can set the of numbers equal to one another. Just like if you make the bases the same in an exponent. Just like if we make the bases the same in the exponent, you can set the exponents equal to one another. If you make the log bases the same, you should be able to set the of numbers equal to one another. Here's what I mean by that. If I just add log of 2x over 3 over to the other side, this is what I get, right? Because it's a 0 on the other side. So that means I should be able to take 72 is equal to 2x over 3. Yeah, and this works. I multiply by 3 and then divide by 2, I do get 108 is equal to x.
Where do you get 108 on this side?
On this side?
Yeah.
From over here. This is the side work. I was dividing the fraction. So it's kind of like almost the same exact thing over here, you know? I would be dividing by 2/3, or just really multiplying by 3/2, which is kind of like what I did over there. So yeah, the same rule applies that if you make the exponent bases the same, you can set the exponents equal to one another. If you have the logarithm bases the same, unfortunately you can't really make the logarithm bases the same. But if it just so happens that you have two things on either side of the equal sign where the logarithm bases are the same, you can set those things equal to one another. And actually, I do that right here. Look at 13. That's the method in doing 13. If you just end up setting 3 minus 4x equal to x over 3. Yes, Henry. Yeah. So for number 12, this is the route that I took on the key. We got log base 3 of x to the 9th is equal to 12. All right, we know that an exponent on the outside of a log can be brought forward and here put in front of the log. So 9 times log base 3 of x is 12. All right, well, if it's 9 times the log, I just divide it over to the other side. So log base 3 of x is equal to whatever 12/9 is, right? I divide by 9 to both sides, and that'll give me 12/9. Divide both parts by 3, that's 4/3. And now I just take it from logarithmic form into exponential form. 3 to the 4/3 power is x, and now we just have to figure that out. You just go to your calculator and type in 3 to the 4/3. Looks like it's 4.3 repeating. Other ways that we could have done that, we could have taken, right off the bat, we could have taken it from logarithmic form into exponential form. We could have said 3 to the 12 is equal to x to the 9th, okay? And then evaluated it that way. Because we have our calculators, we could have taken whatever 3 to the 12th is and then taken the 9th root of 3 to the 12th. And that would be what x is. Let me flip it over on the next page. There's 14 and 15. Yeah.
How do you do 59 x over 2?
Just really treat it like 50 times 1/2 x.
Okay.
Yeah, because x over 2 is really just like 1/2 x.
Okay.
1/2 times x. And then let me scroll down just a little bit and see if we can see the end of 16. Let's see. That's way too far. Okay, I'm probably going past where people move. I'll leave it there for a second. For number 16, I'm glad if we got to this point, and I bet from here on, we could have done it a variety of different ways. Like if you could have chosen to do the quadratic formula, you probably did not complete the square because that's a fraction. But you probably could have used the quadratic formula. However, to clear fractions, I teach this to my algebra 1 students. To clear fractions, if you've got something as in tenths here, you could just multiply everything by the LCD, which in this case the LCD would just be 10. So you can multiply everything through by 10 just to clear out the fractions. And I believe that's what we do here in 16. Yep, that's what I did. You multiply everything through by 10 to get 10x squared plus 3x minus 1. and then the factors. But again, if you wanted to do the quadratic formula, that would be just as good, just as balanced. I know you guys kind of like to use the quadratic formula more than trying to do that factoring by rewrite method, or the master product method anyway, so go for it. Yeah, Joe.
So where the second log where it's log x plus 1, is the plus 1 not a part of the log? Because like we could multiply by 3 when it's part of the log, but then it's subtracted by 1.
Right. It would have to look like this if that one was in it. Okay, it would have to look like there was a parenthesis around the one to be included within the log. See, because there is no parenthesis right here, you assume that this is the parenthesis. Okay, so the plus 1 is not really part of the log. That's why we subtract it over to the other side. Anything that's not within the log, any whole numbers will move to the other side. Any of the logs will combine by way of either multiplying or dividing with their text. All right. Any other questions on the homework that we'd like to talk through or go over? All right. Let me get the guided notes for today. This is section 7.5, exponential equations and inequalities. More inequalities today. And I got to be honest, it's not a lot of notes. Look, the guided notes is literally just a problem. No, thank you. Thank you. No, thank you. There you go.
Thank you. It was so confusing. We were trying so hard not to make it like when you see something, and I go to my class, thank you. It was so bad. It was so bad.
All right, people, here we go. Now, look at the directions. It says use a table and graph to solve. You know, this is a logarithmic equation, right? That I could solve algebraically, totally. And this is a logarithmic equation that I could solve algebraically. However, I want to show you how you would use your graphing calculator to solve this. Now, fair warning, the test, which is going to be next week, the test over chapter 7 is going to be 2 parts. It's going to be 2 days. 1 day, no calculator, 1 day, calculator.
Like no calculator at all?
You know, I think we just make this one a red.
Okay, good.
I think. I don't know. I'll have to talk to you.
You test my brain activity way too much. I think I can do 2 tests too.
Especially like 8 in the morning.
You know, there is science to say though that like if your brain is in a certain mode when you learn that material, it should be in the same mode when you evaluate that. Like,
So mine's on at 7 a.m. and has on at 4 p.m.
right. So yeah, you shouldn't take a test later in the day of things that you learned early in the morning.
My brain still doesn't.
My brain doesn't have time.
My brain doesn't.
All right, so again, there will be a calculator versus, graphing calculator versus non-graphing calculator portion to the test. So this would be on, like if you had your graphing calculator, you could use this. So let me show you what I mean. Now, we've done things like this before when we worked with word problems, before we knew how to evaluate these things. Okay. Come on, calculator. Come on, there it comes. So all we're really going to do is just take the left side as our y1 and take the right side as our y2. Okay, I'm going to take this side as y1. I'm going to put this side in blue. And if you want to change your colors on your calculator, you can do that. And this side as y2. Me, I don't have that fancy fancy calculator. I'm just gonna have to plug things in. So I've got log. Now you can only use. Actually, can you change the base? Can you do that whole change base thing in your y equals? You can. You stinkers. Oh man.
I'm gonna cry, or I'm gonna steal
That's
one of your
okay.
guys' calculators.
Now, see, because I have to assume that at least a couple people in the class, their calculators can only do log base 10 or log base E, which we'll learn about in section 7.6. Our calculators can only do 2 different log bases. I'm only, if it's on a graphic calculator portion, I'm only ever going to give you log base 10 or log base E, which again, we'll learn a little bit later. So, because I have to assume that you cannot change the base. So I've got log of x plus 70, and let's do 2 times the common log of x over 3. All right, I'm going to zoom 6 to get it back to my standard 10 by 10 window. And it looks like I just see a horizontal line running across, and then a logarithm, a standard looking logarithm, and then a horizontal line. Now the horizontal line came through first, which means that looks like it's probably the x plus 70. But wait a second, is a logarithm a horizontal line? No. So that's weird. Think of this in terms of transformations. I know we haven't learned them yet, but think of this in terms of transformations. What would add or subtract something? A right or left, especially if it's on the inside, right? A right or left. And if this is adding, what do we know about moving right or left? It actually moves left instead of moving right. It does the opposite. So what happened here? Well, think about our original logarithm, just our parent logarithm looking something like this. If this were our x-axis here, whoa, that's a little bit too far over. Yeah, pretty close there. If that's our y-axis, here's our x-axis, something like that. So our parent logarithm had the asymptote at y equals, at x equals 0, at the y-axis. So if I move that 70 units to the left, isn't the asymptote going to move 70 units to the left as well? So I'm going to have to manipulate my window a little bit. What I see here is really just, like this is what I'm seeing on my window. Like that's my window right now. I only see something that looks like a horizontal line because I'm only seeing the far right side of the logarithm. So I need to manipulate my window a little bit. Okay, I need to make this, okay, if this moved to the left 70 units, let's go 80. Let's see if that works. There's my logarithm, and there's my other one as well. Now, I need to see when these things are going to be equivalent. Now, what do you notice here? You don't see this piece of the logarithm, right? When I look at my calculator there, you don't see that piece of the logarithm. And you want to know why? Well, actually, yeah, your guys have stopped too, good. Because your calculator is, again, a very dumb, smart object, right? All it's doing is running values and running values and running values. But the calculator assumes that if the number gets small enough, it ends up just being 0. It ends up just going away. Here's what I mean by that. The calculator is running numbers, and it got so small, and it got so close to being negligible, it got so close to being 0, that it just kind of decided it was going to stop. That's why you see your calculator stopping. See, our brains are smarter than the calculator. We know what it should look like. So we have to combine what the logarithm should look like to what it actually looks like on your calculator. Okay, your calculator is not showing this piece of the logarithm. You kind of have to add that in. Okay. It is also not showing it here as well, but it almost just looks like it's the axis. Now, I want to know when these two things are equivalent. So what I'm going to do is find the intersection point. However, doesn't the intersection point have to be on my screen to be able to calculate it? So I got to zoom out a little bit. I could either zoom out or try to manipulate my window so that I see the intersection point. Let's just do that. Let's just change my window. I know I got to go further right. So I went to negative 80. I don't know. Let's go to positive 50. Let's see if that's going to work. There's my first logarithm. Here's my second logarithm. Oh, do I see my intersection? Sweet. The answer should have been yeah. Second, calculate intersect. Choice 5 is intersect. And I go enter, enter. Uh-oh. It's not coming off second curve. What's going on? What? If I just keep hitting enter, will it work? No. What's going on here? Look at where it says x equals underneath second curve. Negative 15. Now, my left side of this equation, will that evaluate at negative 15? Yeah, because negative 15 plus 70 is a positive number, that's within its domain. However, negative 15 divided by 3 would be negative 5. Can I take the logarithm of a negative number? No. So it's trying to evaluate the logarithm, this right side, this piece over here. It's trying to evaluate that logarithm when it's a negative. So we just have to, guess what we just literally do? We just hit the right arrow until it's defined. There it is. Now it's picking it up. You see it? Did you see the trace come in? Yeah. You just have to keep hitting the right arrow until the x value is defined within that function. Okay, now I can hit my second curve, and now I'm going to be able to guess. Okay, there it is. So that means that x equals 30. X equals 30. There's going to be a lot of not a lot of work shown on your papers today. There's a lot of it's going to be within your calculator. So if you want to sketch your graphs, you can do so.
Why did you give us some room?
I don't know, because there's only 4 problems, and I was going to use this paper anyway.
What you did after you put the logarithm
Yep.
and then you did the 70 thing?
Yeah, I changed my window. You can just click on window, and you can change your window manually.
Okay.
Yeah. Okay. All right, well, let's try another one. Shall we? See, that was equality, though. Now let's get into inequality. When two things are not equal. Like 2 to the x and 2 to the 4x minus 1. Okay. So I'm going to do the same thing. I'm going to put the left side in as y1. This is going to be my y1. And then I'm going to put the right side in as y2. All right, so let's go into our calculators here. Left side is y1, so 2 to the x. Our parent exponential. And then 4 to the, and then I'm going to use parentheses when I do this, x minus 1. Some of you guys, it actually goes up in the exponent, but mine doesn't do that. Initial story. I'm going to zoom 6. See, I know I've messed my window. So what I'm going to do is I'm going to go zoom 6, get it back to my 10 by 10. Okay, here's 2 to the x, and here is 4 to the x minus 1. Okay, so take a look here at what I've got. I'm going to trace along this thing with some colored lines here. Here is 2 to the x, and here is 4 to the x minus 1. Okay, now, what I'm looking at here are 2 exponential functions, right? 2 exponential functions. They look like they cross at one spot, but I want to know when the y values, for what x values, do the y values of my blue line end up being greater than the y values of my green line? Thanks, green and then red. Sorry about that. I want to know when the values of y1 are going to be bigger than the values of y2. Now, when I'm looking at the y values, when I'm looking at it on the graph, I'm saying, okay, that means above and below, right? When I'm looking for y values and I want to know when one's greater than one's less than, I want to know above, below. So when is the blue line on top? basically? When is the blue line bigger than the other line? Red / green. Okay, now, I know there's a critical point here. I know there's a point where it overtakes. Let's first start off by finding that. Now, we could find it algebraically by setting them equal, but since I've already got them graphed and I see the intersection point on the screen, let's calculate it real quick. Second, calculate intersect. Now, I'm not going to have to do that weird business where I've got to trace over because this is an exponential, and exponentials are defined all real numbers for its domain. So I'm just going to be able to hit first curve, enter, second curve, enter, guess, enter. And here is my critical point. At x equals 2. That's where it crosses over. That's where it crosses over from one to the next. Now, I just have to figure out, is it all values to the right of 2 or all values to the left of 2? Is it x is less than 2 or is it x is greater than 2? I know at 2, it switches. One goes greater, one goes less. Now, I want to know when the blue line is on top of the other line, right? So that means for all points over here, right? That's when the blue line is on top. Well, that means for every point this side of 2, that means that my solution is x is less than 2. Now, you may be thinking to yourself, based on the original graph, it almost looks like they converged. It almost looks like they meet again. However, take a look at your table. Does that actually happen? Does it actually connect up again? Well, if I go look at my table and I just keep decreasing in my x values, and I could go on forever in my x values, does my y1 ever cross back underneath my y2? No, it looks like my y1 is always bigger than my y2. Will it ever change? Nope. Not from what I see there. It's never going to change. y1 is never going to cross back underneath y2. Okay? Why is that? Because the base is bigger for y2. So that means that it's getting smaller faster as well as getting bigger faster. That's why it's a steeper line on the right side, and it goes closer to our x-axis faster on the left side. So the answer is just x is less than 2. X is less than 2. Let's take a look at another one here. Now, this is the first one that we're mixing functions. You know, the first one was 2 logarithms. The second one was 2 exponents. What is this one? This is an exponent and a linear function. That's weird. This is an exponential function and a linear function. Let's see what this looks like. I'll go to my y equals. I'm clearing out what's there. I've got 2 to the x plus 1. And then I've got 8,192x. Now let's kind of analyze this before we hit graph here. I've got an exponential function with a base of 2. So like very close to our parent exponential function. And then I've got a linear function. What's the slope on that linear function? Really big, 8,192. So up 8,192 over 1. Up 8,192 over 2. What's the y-intercept though? What's the x and y-intercept? 0. So just go through the origin. Okay, now let's actually do zoom 6. Okay, there's my exponential, and here's my linear. Oh. Did I even see a linear function coming across? No, why? Because it's so steep. It's so steep that it doesn't even look like it's there. It's so steep that the line looks like it's the same thing as the y-axis. All right, well, maybe what we'll do is zoom fit. That's another good way to try to manipulate our window. Let's try to zoom fit and see if that works. Oh, perfect. There's our linear. But where did our exponential go? It went away, didn't it? It's gone. All right, so I need to do something so that I can see my both exponential and logarithm, okay? I need to do something so I can see both my exponential and my logarithm. So let me change my window a little bit. Ooh, see, look at my y minimum and y maximum. 82,000. Yikes. 82,000. Let's change that a little bit. Let's change my, let's make that just like negative, let's try negative 100 and see if that works. And positive. Do I even need, I don't even need the negatives. Look, I don't even need the negatives. Let's go negative 10 and positive 100. Let's see if that works. Nah, that's not going to work either. I see my exponential again. See, I need to see, I really do need to see, because it's going up 8,192 over 1, right? So I really need to see something really big there. But I would need to go more, because 8,192 over 1, right? So maybe I gotta go big. Right. Let's make this like 27,000. Because that's going to give me at least 3, up, over, up, over, up, over. But I'm getting closer. Because now I see my exponential. See, I need more x values now. I need to see my x values a little bit more. So I'm going to change my window, and I'm going to go x max. Let's go 20. Let's go 30. I'm trying to teach you guys to manipulate your window. Okay. Now, I'm on the right track. Because do I know where my intersection is going to end up? Yeah, I see. I could, if I extended those lines beyond the graph, I know that it's going to end up somewhere that, ooh, it's not supposed to curve back inward. But I know that it's supposed to end up somewhere over there, right? But so I'm on the right track. Let me just zoom out. Let me see if that works. Zoom, 3, enter. Oh, I'm almost there. Zoom, 3, enter.
It did not work.
Oh, it might have. Let me change my x's. Joy's like, no, I'm doing this. 60. Let's go to negative 60. Da, 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 da.
We did that for a long time.
I know.
I would have tried twice. Yeah, called it a day.
But the thing is, you gotta try to keep manipulating your window. Now, here's what I want to point out. If I were just to think about the basic exponential and a linear function, but a steep one, that's my linear with a positive slope, right? So I should see something like that in the end. Guys, you've got to start visualizing what these things should look like. Because in the end, that's what you're going to try to make your graph look like. Now, this is kind of hard to see because we have our axes are really dark and deep in here. You know you can turn that off. If you go into second zoom to format, you can turn off your axes so that you can see it a little bit better. So there's my exponential, and there's my linear. Now, what are we seeing now that we did not see before? we're seeing a second intersection point. Not just one intersection point, we're seeing a second intersection point. We see two places. Now, take a look here. This is my y1, this is my exponential, this is my blue, and I'll put this in purple. This is my linear. Yes. I want to know when the blue is vertically above the purple. When is that happening? Well, that's happening for all points here onward and for all points here onward. Right? It's happening in those two locations where they cross. Those are those critical points where it goes from bigger to smaller. So it's happening at those locations. Let's first start off by calculating those intersection points. Second, calculate intersect, choice 5. First curve, enter. Second curve, enter. Guess. Okay, it's right there. Good. Okay, the x value is 2.44 times 10 to the negative 4th. And then I've got to calculate my other one, because I know it's going to intersect twice. First curve, enter. Second curve, enter. Now I'm just going to guess over toward the other one. 16. What a nice round number. So I see that this is happening at 0.000 244. And this is happening at just plain old 16. Okay, I want all x values to the left of that 0.000244 and all values, x values to the right of 16. Anything be in between that decimal and 16, y1 is going to go less than y2. Right? That's the only location where the purple line is above vertically the blue line. So my answer really is x is less than, and I should write it out a little bit better here. X is less than 0.000244, or x is greater than 16. And can we say or equal to? No, because they're dotted. This is a dotted line technically. Open circles. Okay. Well, that was fun. So what is this all about? You know, normally you guys think of, oh, using your calculator has got to be like a shortcut. Guys, I would rather do this algebraically, honestly. Well, the problem is with a lot of these, some of them might be impossible to solve without technology, without these things. Okay. What time is it? I'm gonna stop there. We won't have to do this last one. Homework is up here on the board, page 526, 21 to 33 odds, 34 to 39.
Bye.